solving systems of linear equations is what we're going to be focusing on in this chapter. When we talk about a system of linear equations, actually, it can be a system of any equations. We're talking about equations in the same variable, two or more equations in the same variable. And a real-life example of this is what we did for the problem of the day today, where we knew that Farmer McDonald had goats and chickens with a total of 20 heads and 64 legs. And we want to know how many of each. So this situation can be described by two different equations. We know that x plus y, chickens plus goats, or actually let's see, goats plus chickens is equal to 20. And we know every goat has 4 legs, and every chicken has 2 legs. And that has to be adding up to 64. So this is called a system because it's two equations, and in each situation we're talking about the same goats and the same chickens. So what we know is that in the end there were 12 goats and 8 chickens. And the reason why that's a solution to the system is because it makes both of these equations true. 12 plus 8 does equal 20, and 4 times 12 is 48, plus 2 times 8, 16, equals 64. So the solution to a system of equations is the x and the y that make both or all equations, works for all equations in the system. And we're going to learn several different ways of doing this one, which perhaps is the most impractical, is the graphing method. And the graphing method is based on a really, something that I hope that you got the idea of last time. And that is a really simple equation. Let's say y equals 2x plus 1. Well, I know how to go straight to the graph, but I really want to make up a table of solutions, like the function game. If I plug in 0 for x, then y is 1. If I plug in 1 for x, 2 times 1 is 2, plus 1 more is 3. If I plug in 2 for x, 2 times 2 is 4, plus 1 is 5. So that means that each of these is a solution. The point 0, 1 makes this equation true. 2 times 0 plus 1 is equal to 1. So 0, 1 is a solution. 2 times 1 plus 1 is 3. So the point 1, 3 is a solution. 2, 5 is a solution. And as we know, this is a linear equation, and therefore, when I draw the graph of it, it makes a line. And unfortunately, on this thing, the lines don't work so well, so I'm going to do my best to draw a good line. And what I know is that every point on this line, well, if it were accurate, is a solution to the equation, and every solution is a point on the line. Using that basic idea, I graphing method, and that's the first one we're going to learn, the graphing method. So, if I know that, let's say one of my lines is right here, and I'm going to have a little bit of trouble because of this problem with lines. Well, let's just say one of my lines is defined by these points, and I graph another line that's defined by these. Let's say right here, these are all points on this line. And for right now, we're going to leave the idea of what this equation is alone. But if this is a picture of all of the solutions to one of those equations, and this is a picture of all of the solutions to the other, it stands to reason that the point of intersection is the solution to the system, because it's a solution for both of them. So in the graphing method, the first thing you want to do is put your equations into slope-intercept form. Y equals mx plus b. And hopefully you remember how to do that. Then you want to graph them. And then any points of intersection are solutions. So the point, and I will tell you it could be either one point, or if this happened to be a parallel line, there would be no solutions. Or if two of my lines were exactly the same, there would be infinite solutions. So any points of intersection are solutions. So let's see if I can do this neatly enough to illustrate well. Equations are 2x minus y equals 8, and x plus y equals 1. Oops, x plus y equals 1. I better add my little graph thing here. Okay, so I first need to solve for y, because that's what slope-intercept form is. It is y equals mx plus b. Okay, this is not really quite working. Y equals mx plus b. Hopefully you remember that well enough. So minus 2x from both sides. Negative 2x, oh, sorry. So that gives me negative y, or the opposite of y is negative 2x plus 8. And from there I know if the opposite of y is negative 2x plus 8, then y is 2x minus 8. It's the same thing as multiplying the whole equation by negative 1. So here's where you have to remember how to graph. You go down 8, because this is the y-intercept. Go down 8. 1, 2, 3, 4, 5, 6, 7, 8. And from that point, you use the slope, which is 2 is the rise over run. So I'm going to go up 2 over 1. And I can do that as far as my graph goes. And I'm not even going to try to draw the line because I don't have a straight edge and it's not going to be accurate. So again, I want this to be in y equals mx plus b. So it's going to be negative x plus 1. And remember, the coefficient of negative x is really negative 1. So the rise is negative 1 and the run is positive 1. So I first graph my y-intercept. And from there I'm going down 1 and over. Down 1 over 1. Down 1 over 1. Down 1 over 1. And we can see that this point right here is the point of intersection. And just so you remember that that is the point 3, negative 2. Because when I'm graphing points, I go across first, that's the x, and then up and down, that's the y. Unlike slope, which is rise over run, I do the y first. The way I remember this is that I'm thinking rise over run. So this is going to be the rise, and this is the run. When these are right next to each other, though, they're horizontal, I do the horizontal first. Okay. Sometimes you're going to get problems that when you graph them, you get lines that don't necessarily match exactly. Let's see if I can make one up that does that. Let's say that this is one of the lines, and this is another line. You can see that they intersect, but you can't say exactly where that intersection is because it's not on a bullseye or a lattice point, as we've known. So it's somewhere in here, and I'm just going to estimate, and that's what you're asked to do. Estimate. That looks somewhere, and in your homework it says estimate to the nearest half. So that looks like approximately 1/2 and -1/2. In our other methods, we'll be able to find out more accurately, but sometimes you just have to eyeball it and say, especially when the directions say, estimate that. Similar to have some that you have to, oh, sorry for my slanty thing, but let's just say the parabola, one of them was like this, and one of them was like this. Okay? Again, it's wherever these points are. I think in your homework, they're actually on lattice points, but you don't even have to do any math for these. You just look and you say, where is it intersecting? This one is about, this looks like about 3.5, -1, 3.5, -1, and this one looks like about -1.5, -1/2. And the only other tricky thing is, as I said on the first page, if graph things and you get, in the end, let's say this is my line. Whoop. Oh, I thought that was supposed to be done. Say that's my line, and then I put the next one into slope intercept, and I end up getting the same exact line. That means you have infinite solutions. Finite solutions. By the same token, that's the same line. If you have a parallel line, parallel lines never cross. So that means no solution. There are no solutions in common. And that's that.